Now we come to qubit representation, how we can represent a qubit state. A quantum state of a qubit or any particle can be expressed analytically. For example, you can have psi of x equals to a sine kx plus b cosine kx, and a and b are constants. K is the wave number. In this expression, the psi of x is an analytical representation. So we can have sort of analytical formula to express the quantum state. However, we can have an alternative representation called vector representation. And in the vector representation, we look from a different perspective on the quantum state as a living vector or an object in a computational or an Hilbert space. It means that we can say, okay, we ask ourselves this question: what are the fundamental components that compose this particular space? In our case here, we have two components. We have the cosine k of x and we have the sine k of x. Then, if these are orthogonal to one another, and also, of course, orthonormal, so if the state is normalized, then we can say that the psi of x would be represented as in terms of a kit notation, which we are gonna define shortly. To the kit here, it means that we are saying that the psi state is expressed as a quantum state represented by a vector. So this is inspired to, this is what Paul Dirac has put forward to represent a state in terms of its components or individual components, which are orthogonal or fully resolved, using the vector notation as a vector in a space. So the projection of this vector in a particular space would represent how much of these components are in the vector represented the total state. So this is the vector represented the total state, and then we can have A, and then we can have these fundamental dimensions of this space, which are k of x plus, and then we have B on the other dimension, which is cosine k of x. In this way, we can write the quantum state as a vector, which means that psi will equal to two numbers. We have A and B. So A is the coefficient on the first dimension, and B is a coefficient on the second dimension. In that sense, we can understand the wave function as a vector living in a Hilbert space or a quantum space. The dimensions of this space are composed of the fundamental components, which can be fully resolved or they are orthogonal to one another and can compose the state. That's what Paul Dirac has put forward. That's easy to represent quantum state in terms of Dirac notation. So if you have for a qubit, this means that the qubit is a two-dimensional living object. It's two-dimensional quantum state. So it means that it composes out of two-dimensional states. So we have alpha, and then we have 0 plus beta, and then we have 1. This is called the kit, and the kit means that now we have the state taken to be expressed leveraging the vector notation. Then if we would like to represent this as a vector or a column vector, then we have alpha and the beta, and immediately we understand that this location corresponds to alpha, which is next to the kit 0, and the beta is the component or the coefficient next to state 1. And this is what we can see here, that we have the qubit in terms of alpha and beta could be represented as vector. Okay, so why this is important? Because now we, instead of writing fully entangled mathematical expressions that are very complex, we can express them in terms of a space. We can look at them as a space. And then in that sense, we can represent them with coefficients in a column vector where each number is corresponding to or expressing this coefficient next to a particular state or a fundamental dimension of this space. And instead of writing it, we can just stick to what we have here, that expression of the vector representation. And now we come to how this was inspired. So Paul Dirac thought, okay, maybe we can borrow the analytical representation or the analytical way of writing vectors in algebra or analytical geometry in 2D and 3D space, and in that sense, leveraging the same methodology to express a quantum state, which is composed of small eigenstates, or which we call it the dimensions of a particular Hilbert space. So in this sense, we if we have a vector A, that vector has two coefficients. So it can have ax, I, plus ay, j. How does this come? Because if we have here this two dimension, we can have here x, y, then here we have the I, and here we have the j, and this is our vector A. So we can express it in terms of Dirac notation like this. Similarly, if we go to 3D space, we can have the same methodology. You can have a vector B, which has all of these projections on the x and y and the z, and this you can express it as a column vector. That's normal. I mean, it's normal analytical geometry and the linear algebra. So you can have the coefficient bx, by, and bz representing the projections of the vector b on the fundamental axes of this space, the fundamental dimensions. This is a Euclidean space formed out of three dimensions. So we have bx, which is a projection on the x-axis, by, which is a projection on the y-axis, and bz, which is a projection on the y-axis. And in terms of Dirac notation, the vector b can be represented as bx I plus by in j and plus bz in k. If you go to the qubit representation, this is what inspired Paul Dirac. We can also express the quantum state of a qubit similarly, and then we can express it as a living object in 2D. So in that sense, you have the qubit q, which can be expressed as alpha 0 plus beta 1. Then you know that this state should be normalized. So normalization would be alpha squared plus beta squared that equal to 1. Then if we want to express it in terms of column vector representation, we have two numbers now. We have the number alpha and the number beta, where as we have seen earlier, the alpha is corresponding to ket 0, the beta corresponding to ket 1. So this is space. Now we can express also this fundamental space. So the qubit is sort of living in two-dimensional space. So this is q, and this is 0, and this is 1, and here are the projections. So we have the projection here alpha, and here we have beta. So the qubit is a quantum state in two-dimensional space because it's a two energy level system. So we have the 0 state and the 1 state. Sorry, this is 1. And together they form the qubit state. So what if the qubit is entirely 0? So we end up having the 0, which means that we have 1 here and 0 here. So the total probability of this is 1, is 100%. So this is one of the expression of the fundamental dimension ket 0. Then we can express 1 as 0 and 1. So this means that 1 times 0, and of course we have 0 times ket 1, so it does not exist. And here we have 1 times ket 1. So we can make it more clearer by writing it. And here we can write, here we end up having 1, and here we end up having 0. So in that sense, we can express the fundamental dimension of the Hilbert space of the qubit. As we see here, we see here the expression of ket 0 and the mathematical expression of ket 1. And this is a geometrical representation, which I have outlined now here on my notes. And we can learn more about the properties of this. Like now, the ket is a column vector, definitely. So the ket is a column vector. So we express it in a column vector like this. It has a component alpha, component beta, and this is our column vector. If we make the transpose, which means that we have the row vector or the pseudo vector, then we have the bra. So together they form the bracket, as we are going to see now. So the bra is actually the complex conjugate transpose of the ket. So we get up a row and of course the complex conjugate of these numbers. And if we got the dot product of both, then we have the row, which is the bra, and then we have the column, which is the ket. Together we get 1, and this is why it's called bracket, bra and ket notation. Let's see it now analytically on the board. So you have here psi, which has a two component, alpha and beta. Then we can have the bra, so it's the ket, can have the bra, and the bra is actually the reverse. Then we get the complex conjugate transpose of this one. Then we have alpha star, beta star, and together, if we put them together to get the normalization, we get alpha, we get psi, and we get bra psi and get psi together. This would mean that we have the pseudo vector of the bra of psi, which is alpha star, and beta star. It is multiplied by the column vector, which is alpha and beta. And together we get this times this, we get plus beta star beta. And this will give us alpha squared plus beta squared. And this should equal to 1 if the state is normalized. If the state is not normalized, then you have to normalize it. Furthermore, we can get the outer product, and the outer product of the kit and the bra would be, we have the kit first, then we have the bra, which means that we have the column vector of alpha and beta times pseudo vector alpha star beta star, and this will give us a matrix now of alpha squared, alpha beta star beta, and beta squared. And this is called the density matrix. And of course, now we have in this matrix, we have good properties. These two numbers represent the probabilities of measuring the qubit to be in 0 or 1. Based on this number, if we run the experiment many times, you would know how many out of these experiments, when you measure, you will find the qubit in state 0, and how many you are going to find the state in the qubit in state 1. Those are the off diagonals that represents the other states. But what matters now, we have the diagonal ones, which are correlated with the probability.